Okay, good morning, everyone. I'd like to welcome you to the CCRO System Design Using LewaPlus training webinar. My name is Leanne Hersey. I'm with Desalitech. I'll be moderating today. We'd like to go ahead and welcome Alan Sharp from Lanxess, who will be presenting today. He's been in the water industry for over 45 years and has worked at Lanxess for the past decade in several roles, including design software, R&D, and technical marketing. Alan holds 2 degrees in chemical engineering and chemistry from Bucknell and an MBA from Temple University. If you are in the water industry, you probably know Mr. Sharp. He's been a well-known figure in the industry and has published numerous technical papers and presentations to educate the water industry and its clients. We'll also be hearing from Brent Stewart of Desalitech today. He is our lead applications engineer. His previous 13 years of work focused his experience exclusively in reverse osmosis on the process and application side and project management. He holds engineering degrees in environmental engineering and an MBA from the Polytechnic University. As I mentioned, he's our lead applications engineer here at Desalitech, and he's leading the development of incorporating our CCRO process and technology into third-party RO membrane and anti-scalant softwares such as Lanxess's LewaPlus. Today's webinar is going to be comprised of several parts. First, we're going to hear from Alan on Lanxess and his LewaBrain membranes. Second, we're going to hear from Brent covering the CCRO process. Hopefully many of you are already familiar with the process, but we will go through briefly the differences. Then we're going to cover the actual CCRO module within LewaPlus, and we will have a lively Q&A, so feel free to queue up many questions as they come up. Type them into the chat box, and we will answer as many as we can at the end of the presentation. Now I'd like to pass it over to Alan. Welcome, Alan, and thank you very much for joining us today.
So, good morning or good evening, depending upon where you are. My name is Alan Sharp, and thank you, Leanne. And thank you, Desalitech, for this opportunity to actually speak and work with Desalitech on their innovative CCRO process. For those of you who have been in the RO industry for years, maybe Lanxess is a newcomer to you, and I thought I would just mention that Lanxess has been in the RO world for, I guess around 10 years now, commercial production starting in 2011. But you may be familiar with Lanxess because we have been involved in water treatment for years and years through our LewaTit ion exchange product line. So doing ion exchange is advanced polymer chemistry, and doing RO is much of the same. So what I would like to do is briefly just introduce the LewaBrain chemistry that is embodied in our RO portfolio, and then we will move into the design phase. But all of the LewaBrain elements that you will find inside of our design software, LewaPlus, can be applied in both classic RO and in CCRO. So let's go to the chemistry, and I urge you to watch the. Before we get to the chemistry, let me just start with a kind of an interesting slide. This is where it all starts in RO systems. Lanxess is a provider of reverse osmosis membrane, and this gets embodied into a device known as an RO element. And from the outside, the RO element looks pretty much the same from manufacturer to manufacturer. The key pieces inside the RO element are, of course, the membrane chemistry, the feed spacer geometry of moving the feed water across the membrane, and the fundamental mechanical construction of the element. When Lanxess decided to enter this marketplace, we had a couple of fundamental concepts to differentiate our product line. And of course, the first is pretty much obvious. You cannot play in this space unless you have modern and fully automated production equipment. and you pay high attention to the purity of the chemicals. The technologies that are embodied in our product come from Lanxess scientists who have for years worked in controlled polymerization technologies. Our concept was also to develop a membrane chemistry that would provide low fouling, long life, and we also test every element. Here's the chemistry, and I urge you to watch carefully at the middle of the slide. What you're seeing here is the actual polymerization chemistry, and if you look to the left, what you will see is the fundamental monomers that go into this reaction. And to tell you the truth, these monomers are pretty much the same from manufacturer to manufacturer. It's how we build the functional polymer that is a differentiating piece. In the case of Lanxess and our chemistry, we have purposely decided to build a polyamide barrier layer of high cross-linkage. And we do that because on the right side of the slide, you will see that carboxylic that's circled in the middle. By generating a polymer of high cross-link density, we can suppress the carboxylic, and that lowers the surface charge in the membrane. RO membranes would be pretty simple if there were not carboxylics present, but that carboxylic provides a functional moiety on the surface of the membrane, and that makes RO chemistry complicated. We purposely suppress that charge because it creates a more dense polymer by going high cross-linkage. More dense polymer means that we can get a little more solution diffusion mechanism in the separation mechanism. And it provides high rejection, and the high cross-linkage also provides higher stability, particularly at extreme pH and temperature. All that said, this chemistry is the same chemistry that is practiced by all the major RO suppliers, and the differentiation between the product lines is related to things such as spacer geometry and charge on the surface. So let's take a look at the next slide. This is an attempt to explain a little bit of the differentiation in the chemistry. This is a paper that we presented in South Africa. It's a couple years old now, but the data in it is quite interesting. If you look at data sheets for RO membranes, what you always see is standard tests conducted with sodium chloride, usually at 2000 ppm, hydronautics at 1500 ppm. And sadly, the real world is full of mixed ions, and waters can have molecules or ions like borate and silicate, nitrate. And if you look at the very middle of this slide, this is an attempt to show you different chemistries from different competitors play out. For the most part, sodium chloride rejection, fairly classic, 99.8. But if you look at boron, silica, and nitrate, you see different rejection properties for these different membranes. And that reflects a little bit of what happens in field conditions. If I move to the bottom of this slide, I'd like to talk a little bit about this piece of data right here, where we actually challenged the membrane with 100 part per million of IPA. In this case, we first test the membrane for sodium chloride rejection, and you can see LewaPlus is on the left, a competitor is on the right, and but you can see for sodium chloride, the competitor has a higher rejection. But for IPA, the rejections are reversed. The LewaPlus has a higher rejection. This is a very interesting experiment because IPA, or isopropyl alcohol, is a non-charged molecule, and it then does not have any interaction with the surface charge of the membrane. What you are observing here is the rejection that is solely driven by solution diffusion. And moving molecules through a more dense membrane is slower, and that slowness, or that diffusional limitation, creates an apparent rejection. And in the case of IPA, LewaPlus actually has a higher rejection. What's interesting here is if I compare salt passage, the salt passage for the LewaPlus is about 3.7%. Salt passage for the competitive membrane is 5.4%. If I ratio those, what you'll find is there's about a 45% more IPA coming through the competitive membrane. So the argument is that solution diffusion does have an impact and does differentiate different membranes. The data on the right, boron rejection, is sort of a testimony to this. Boron's very interesting. At pH 9.2 to 11, the boron, or the borate, is actually a -2 valence. And as the pH gets lower, for example, 7 to 9, the borate is actually a monovalent negative charge. And below 7, it's actually non-charged. So what you see here is a plot of different rejection performances. The blue is a competitive membrane. The red is a Lanxess membrane. And you can see there are different rejection performances based on the pH. This is in fact due to the differences in solution diffusion performance. Lanxess membranes tend to have higher rejections as the molecule becomes more non-ionic. At high pH, you get more surface charge interaction, more anionic repulsion. The net being that these rejections are very close. But the message here is there are differences in rejection performances depending upon the membrane and the surface charge. These differences actually can be monetized in any given situation. If you need a specific rejection, say 80%, you will need to actually increase by adding caustic on this competitive product to get its rejection performance up. So, a little bit on mixed ion performance in real-world solutions. Let's take a look at the next slide. This might be of interest to the people that are in the power industry. Here you have a statistical determination contour plot. These are surfaces because most people know silica rejection performance is a function of pH and temperature. This data is fairly simple to understand because essentially if you look at this box here, you can see that the more red, the higher the rejection. And this is a piece of data for a low energy membrane where you can see Lanxess has a much greater percentage of red in its rejection profile over temperature and pH. And the more red, the better. So it turns out that for bulky ions, things like silicate, nitrate, borate, arsenate, the Lanxess chemistry actually has a pretty good performance. Let's move to the next slide. What I thought I would try and kind of wrap up with is, this is a picture of a product market. These are the common low energy, low pressure RO elements in the marketplace. And you can see, for example, these Lanxess products are low energy and are low energy with a special spacer. Here is the flow and rejection performance and the spacer heights. And I've summarized some of the other products that compete in this low pressure space. This I find interesting because here's a product at 9,200 gallon per day, and here's a product at 8,500 and one at 12,650. And the question that's always intrigued me is how does one decide based on data sheet values which element to apply in a given situation? So the best guidance that I could give you is use the design software, because the design software takes into account the performance of these products under various conditions. On the other hand, there's a shorthand technique. You can calculate the A and B values. A value is a measure of the water permeability of the membrane, expressed in this case LMH, liters per square meter per hour, divided by the applied pressure in bar. Or the B value, meters per second of salt movement through the membrane. These values are more or less normalized values and they can be used to compare to one membrane against another. It gives you a clue as to the permeability or the water movement through a membrane and the salt movement through the membrane. Higher values here are good. Membrane permeability is high, more throughput, and higher values here are not necessarily good, they're bad, more salt passage. So you can look at this array of different flows, and by going over to your A and B values, you can more or less get a sense of how these membranes compare to one another. What I would tell you here is these membranes are all competitive with one another. These are products that all can compete in the same membrane space. So let me conclude with a couple of quick things. Lanxess introduced a novel spacer using alternating thick-thin strands, 34 mil spacer height, and that's been available to users for about a year and a half now. Our initial placements in the marketplace have been good. It has a very low differential pressure, and what I wanted to point out here is we market this product for bioaccumulation or biofouling resistance. You're looking at data from a Dutch university where they actually followed the secretion of a metabolite, ATP, adenosine triphosphate. The only way adenosine triphosphate appears is if a living organism secretes it as a metabolite. It's a very unique test method that was developed. The take-home information here is ASD technology, alternating strand technology, actually produced the lowest amount of ATP secretion in a controlled experiment over 9 days. We repeated that test over a 90-day period, and you can see in all cases the total pressure drop increase after 90 days was the lowest, and the total time to increase up to 15% was the highest. And let's take a look at one other new thing from Lanxess, and that's we recently introduced our ultra-low pressure membrane technology. And what you're looking at here is normalized flow and normalized rejection for, again, a product market that includes our ULP, which also incorporates an ASD product, and these competitive products. This product is very useful for municipal application and water reuse application. So I offer it only as something new. If you're involved in those applications, I would urge you to take a look at it, and these products are incorporated into our LewaPlus design software. I assume most of you know this software. It's new and includes, for the first time in October, we released an upgrade with the CCRO module, which Brent will talk about in a minute. And for those of you who have not looked inside LewaPlus, this is a picture of our design screen, which highlights the Run Comparison tab. I think it's a nice piece of technology that makes design decisions easier for the designer. And we have an overview screen that is for the process engineer, sort of a complete material balance with individual points that will indicate the quality, the TDS and permeate, the conductivity of the permeate, and the flow. So a nice piece of technology. And finally, for those of you who are real world, how does LewaPlus compare? This is a quick piece of data from one of our original plants. If you follow the red circles, you will see that on the right side, the LewaPlus projection pretty much matched what the client was seeing. So this has been our experience. LewaPlus is pretty darn good at predicting what's happening in the real world. And with that, I will turn this over to Brent, and let's talk about CCRO. Thank you very much. Appreciate it.
Great. Thanks, Alan. I'm assuming everybody can hear me. So again, thank you, Alan, and thank you, Lanxess, for adding the CCRO module. The program is awesome. So the first thing I want to do is just give a basic process overview of CCRO, and just that basic understanding is going to help you design systems. My slide graphics aren't going to move here. So the main difference with our system is we always have this one stage configuration, and then the only equipment difference is actually this circulation pump, and that boosts the dP, or the pressure loss, across those 5 membranes. So the simplest way, or the best way to think about it, is like a basic sand filter or UF membrane. So during what we call closed circuit, the feed is actually equal to the filtrate. We concentrate up, and then you backwash. But in our case, with RO, of course, we're concentrating up TDS, and then we're flushing that concentrated brine. So it's a semi-batch process, again, during closed circuit, where feed is equal to permeate, and then we concentrate up that salt and flush to drain. So there's 2 modes of operation, closed circuit and PF. So the closed circuit, again, feed is equal to permeate. It takes anywhere from 5 to 50 minutes. And a common theme that I'll continue to bring up is we're replacing stages with cycles. So again, 1 stage, and we're just cycling through to concentrate up the salts versus going through stages. And we're concentrating in time versus space or stages. So the overall recovery is simply a function of the number of passes or cycles through the membrane. So we concentrate up, and then again we flush the concentrated brine to drain, and that's what we call the PF mode. So that takes 1 to 2 minutes, and the PF is triggered by a number of set points that you can change on the HMI, and it really highlights the unmatched flexibility that's inherent with a semi-batch process. So the default is a volumetric calculation. So if the permeate is equal to 9x and the volume of the system is x, so the volume of the system is what you dump during PF mode, then that recovery would be 90%. So 9x plus x, your feed is 10x. And then the other one is, set point is connectivity in the loop. So you can set the connectivity to 10,000, 20,000, whatever, and it will trigger the flush. So the recovery will be a function of however long it takes to hit that set point. And the advantage with that is if you have a wastewater reuse application where the feed is constantly changing, it will automatically adapt without any operator intervention. And the other one is set point is pressure. It's more just a safety check, and then permeate quality. So increased permeate quality, you know, your TDS can increase as you increase the recovery, but you have the ability to maximize your recovery while still hitting your permeate target. So if you set it at 5 whatever ppm microsiemens, you would trigger the PF or the dump when you hit that target. So one of the important inputs, one of the few inputs in designing CCRO systems is the cycle recovery. So while feed is equal to permeate, you can see in the PFD 100 in, 100 out, the recovery by default is 50%. So that means our circulation pump is 100, the feed is 200, and of course 50% of 200 is your 100 GPM or cubes an hour permeate. And that 50% cycle recovery is the same as a traditional system with stages. You know, so if you had a traditional 3-stage system, you know, the first stage would be 50%, another 50% to get you to 75, and then another 50% to get you to 87.5%. And I'll highlight that 1 cycle is the volume of the system divided by the circulation flow rate. So the sequence time is that 1 cycle time multiplied by the number of cycles. And the number of cycles, of course, is a function of the overall recovery. So more cycles, higher recovery. And there's a number of benefits with our patented process, and I'll just highlight a few before I jump into the program. So we really have this ability to push the limits to maximize recovery. So we flush out the sparingly soluble supersaturated salts before they have time to precipitate out. And an example of that is silica. You know, a general rule of thumb with antiscalant, you can go up to 300 ppm in the brine at neutral pH. Well, we've pushed that to 4 and above 500 ppm. And again, the reason we can do that is above 300 ppm, it's only supersaturated or above the 300 for 1 to 2 minutes, 3 minutes max. So before it has time to polymerize, we're flushing it out. So it's only the last 1 or 2 cycles that you see the elevated concentrations. Where in a traditional system, it's steady state. That last membrane would see 500 ppm of silica 24/7. So the other benefit is Cip reduction. We've seen a reduction of 3 to 5x. We have that induction time advantage that I just mentioned, in addition to the feed flushing and salinity cycling, which disrupts scaling and biological growth, providing unmatched reliability and uptime. And the other benefit is energy savings. So CCRO systems gradually increase the pressure over time, resulting in a lower average pressure. So you can think of it in a traditional system if you had infinite interstage booster pumps, and you can run this in a traditional design. If you wanted to add 5 stages and you put a booster pump between every stage, you'll find out it becomes significantly more energy efficient, just from a design and capex, and you would never do it. Lastly, as I kind of mentioned before, the simplified design and operation is just really unmatched flexibility. And I think that's evident in the number of trailers that we've sold. So obviously, trailers can run at 75%. You go to the next site and you want to run it as a second pass in front of a mixed bed, and now you want to run at 98%. So that one-stage design is very beneficial. Last slide before we get to the program. So just a sample list of Desalitech's clients. We're quickly approaching 100 systems, so we've moved past a startup to a successful company. 80% of our customers are repeat customers. ADM and Edison, I can tell you, have over 5 systems. And lastly, regarding awards, most of you probably heard we just received the Aquatech Innovation Award here a couple weeks ago in Amsterdam, and recently voted best place to work in the water industry, and that was a global survey, which is pretty cool. And last year, we were awarded the Breakthrough Water Technology Company of the Year that was announced at GWI's 2016 Summit in Abu Dhabi. And you can go to the website, to the newsroom, for additional information. And I'll just highlight, we put a new video. There's a big box I'll show at the end. You can click on how CCRO works. So it's just a simplified, quick video. So now we'll get into some of the program details. So the previous approach, we used to run 3 projections, and then we would paste those into Excel, consolidate the information. Then I just wrote a macro to generate a report. So obviously, we're quite excited to have this module in LewaPlus. So the way the program does it is it runs a projection for every cycle, which would obviously be time consuming if you had to run that individually. So it just helps you understand how the process works and how the program works. So if you look at the PFD, you've got permeate connectivity over time. So again, we used to run this CC1, or the first cycle, and then we'd run the projection for the last cycle, what we're calling CC2. And you can see everything in between is a straight line. So this is permeate conductivity over time, and the pressure profile is the same. So as we cycle through, we've got a PID loop, VFD with the mag meter. So we keep a constant flux, and to keep that constant flux as the TDS is increasing, you get this perfectly straight line increase in pressure. So we have Desalitech has two standard products. So the standard Reflex, we call it, Reflex stands for reliability and flexibility. The recovery range is 75 to 98%, and the pressure has to be less than 600 psi or 41 bar. So the current module in LewaPlus is the standard Reflex. So you can go down to 50% recovery, but it really is a higher recovery product. And when you run at the lower recoveries, you can contact myself or Alan. Will help kind of to walk through that. But we know we add more value at higher recovery. So for the lower recoveries and higher pressures, we have what essentially is our seawater system, and we call that our Reflex Max. So that's anywhere from 40 to 98% recovery, and that does the full range of pressure up to 1200 psi or 82, 83 bar. So the Reflex Max is a phase 2 that we'll add to LewaPlus. And before we leave the slide, I'll just highlight that product, that Reflex Max. You could use it as a seawater system, and in the same day you could like stick it on the other side of your plant and use it as a second pass RO. So the flexibility of our process is certainly unmatched. So here's a screenshot of LewaPlus. You've got traditional RO, and then below that, highlighted, you can't see it, but in brackets it'll say reverse osmosis closed circuit. You see the RO, CCRO. And we have a number of, excuse me, we have a number of samples. So you can see the top is the closed circuit samples, and the bottom is the traditional. So if you're running at lower flux or lower recovery, brine recovery, wastewater reuse, you may find some of these examples to be helpful. Here's a screenshot of CCRO on the left, and then the traditional design. So essentially, if you're familiar with the program, they're essentially identical with a few tweaks that we'll get into. So what we did, this section was for energy recovery, and since we essentially have no energy, or next to no energy loss in the system, we have no energy recovery device. So we just replaced this section with the CCRO inputs, and these are the only difference in designing the CCRO is these additional CCRO inputs. And I should highlight 9 times out of 10 are easy applications. And when I say easy applications, I would say relatively high recovery and higher flux. You don't have to change these set points. So the times you're going to want to go in and change these set points is brine recovery or wastewater reuse, and we'll get into those details in a minute. The other change is this closed circuit tab. So these inputs give you these outputs, and Alan probably highlighted, but the thing I love about the program is every time you make a change, the program runs, and it's unbelievably fast. I don't know how they got the algorithm to work that quickly, but every tweak, and you have every input change, and you have the output right on the same screen. Some of the other changes are up here. So instead of, we've only got one stage, so you wouldn't see multiple inputs here. And then for the staged information, we have the first cycle and the last cycle, and then we just show the average here, and then the PF mode. So most of the time you can use the default inputs. You don't have to make any changes, and you would just go in and enter the number of pressure vessels, and that would give you, of course, your flux rate. And our default is pressure vessel length of 6 membranes, or 6M. But by default, we only put 5 membranes in that pressure vessel. And the reason we do that is we create more volume. So recall, each cycle is the volume of the system divided by the circulation flow rate. So if you have more volume, that means you have a longer sequence time. So the guideline is 10 to 40 minutes. You can go down as low between 5 and 10 minutes for lower recovery. And the only reason for that is we add more value in closed circuit, and we don't want to be jumping back and forth between the CC and PF mode. On the high end, we're really not concerned. So the logic is we don't want to lose our induction time advantage. But again, if the system was running CC mode for 50 minutes, it's only the last 1, 2, 3 cycles that the salts are really super saturated. So it's not like they're at that high concentration for the full 50 minutes. So the reality is we're not really concerned about the high end. But if you did have high recovery, then we would just fill these pressure vessels. So you could use 90% as a rule of thumb if you wanted to fill the pressure vessel. So when you do that, you lose the flexibility to run at the lower end with a longer sequence time. And I highlighted on the last slide. So again, you're seeing the pressures for the first cycle and the last cycle. So this CC9. So in this case, there was 9 cycles. And then the average information and PF. So I'll highlight the pump selections because I know there's some confusion. So the feed and high pressure pump, there's 2 design points. So the flow rate during closed circuit, the CC average, the reason why this is blank is it's a constant raw feed flow rate. And then as far as sizing your pump on the number of stages or pressure, you're going to take that flow rate, and then you're going to take your last cycle pressure. In this case is the 302. And then during PF, what we do is we increase the flow rate, and I'll get to that here in the next slide. We increase the flow during PF roughly by 20% or 1.2. So if you multiply this 167 by 1.2, you get your 200. And again, I'll get to that on the next slide. But for pump selections, you need to be aware of the two design inputs. So you've got the higher flow, but PF is at a much lower pressure. So it works out in the pump curve. So in general, if you select in the middle of the curve at the most efficient point, you have lots of room to go 20% or 1.2 over, especially since it's at significantly lower pressure. And then the circulation pump flow rate is shown here. And again, that's only boosting the DP across the membranes, which in this case is only 7 psi. Our rule of thumb is we design for 42 psi. And the logic behind that is, if the membranes are 5 years old, or if you have a trailer and you're just kind of pushing the membranes to their end of the life, you want enough pump to be able to overcome the plugged up membranes. And then the guideline is max DP of 40 psi across one pressure vessel. So the inputs for CCRO, and again, I need to highlight the system design is so simple because it's always one stage. You know, there's no interstage permeate throttling or booster pump to get your cross flow on the last stage. It really is simple, and once you start to use the system, you'll see that. But you do have the ability to tweak or have some of these inputs. So if you do want to change the default set points, and you can see the default set points here, 50% recovery, 20% recovery. So that's your cycle recovery, your PF recovery, and then your PF flow increase. If you want to change it, you can click on Enable Configuration, and then you'll have access. It won't be grayed out like above here. So when you click on that, the one thing you'll notice is the default cycle recovery is 50%, but below that says 49.3. So what we've done is we round the cycle recovery to create or we round the total cycles by adjusting the cycle recovery. And the reason we do that is just from a programming standpoint. So in this case, we run 10 projections. So if it was 50, this would be 9.8 or 10.2, and we'd have to run partial projection. So the main input, again, is cycle recovery. So default is 50%. And this directly controls the amount of concentrate flow per pressure vessel, the brine leaving the pressure vessel during closed circuit. So depending on your feed water quality, this is, of course, a higher number. You know, if this was wastewater, you'd want it above 18 GPM. If it's aeropermeate, this would be an extremely high cross flow. And then the PF recovery is the recovery rate during the PF mode, and it's similar to a traditional system. We just have a little bit of back pressure. But the goal of the PF flush, the PF mode, is just to flush out the system. So we really like just to have the low recovery, and it helps with the pump selection. So for the most part, you're not gonna tweak that number. And this 20%, the reason why we came up with this PF flow increase of 20% is we kind of like the cross flow or the concentrate flow per pressure vessel during the closed circuit and the PF mode to roughly be equal. So you'll see with these default settings, these numbers are essentially the same. So I like to see these roughly the same, but for different reasons. So we like the high cross flow, keep our concentration, polarization, our betas low. And then I like having the energy during the PF to really create some turbulence and blast out anything that started to precipitate. But those are the two main inputs. So your cycle recovery will set the amount of cross flow, so that directly controls your circulation pump. And I'll highlight just quickly a couple other things. We've got this Excel export button, which I find handy just to grab the data in the format that I can edit. And if I didn't highlight, I should have highlighted. So during the PF mode, it's a reduced permeate flow rate. But if you wanted to, during PF mode, if you have the same feed flow rate and the same PF recovery, then you could have a constant permeate flow rate. But remember, during the PF mode, the circulation pump is off because we're not recirculating, we're flushing to drain. So if you think back to that PFD where we had half the water being recirculated, you have to increase your PF flow significantly to 100% and then your PF recovery to 50 to get the same permeate flow rate. But if that was a requirement, that's something you can do. And then if you wanted a constant feed rate, if you didn't want to increase the flow during the PF mode, then you would simply make that PF flow increase just 0%. And while we're here, I'll highlight this concentrate tab. So this is just the brine, the same as traditional. But the cool thing is you can come through here and click on the number of cycles. So again, talking about our silica example, you could click here, it would be 8, 7, and you could look at silica and see how many cycles it was above the 300 ppm. And then as you kind of dive into induction time, you could really dial things in here. It's a little bit more for R&D and the PhDs, but it's a cool feature. I'll highlight, so moving away from the design page, and of course the water analysis and general spec is the same. Power consumption tab is the same. You can go in there and change the pump efficiencies, the motor efficiencies, and actually the VFD efficiencies. So it's quite accurate to get your energy calculation. Post-treatment, which is great. You can go in and remove the CO2 if you wanted to increase your pH without adding any chemicals. You know, add alkalinity, caustic, whatever you want to do, and then it'll show that the permeate quality. And then they have this pretty detailed cost calculation where you can go in and estimate CapEx and OpEx. The one thing I'll just highlight about that is in the operating cost tab, you can enter in the cost to supply and dispose of water. So this is the GWI average in the US for last year. And if you look at, if you compared it to a traditional running at 75% recovery, and we had done this design at 90%, you know, you save a lot of water, but more importantly, again, this is just the GWI average for the water tariffs. The cost savings would be $300,000 per year. So there's a lot of value in high recovery. So we're getting a little bit short on time, so I'll just go through the report here relatively quickly. So we tried to keep the format the same. You'll see this section with closed circuit details. So you had your inputs over here, number of cycles, sequence time. A couple additional outputs is the system volume and the permeate volume per batch. And then down here, instead of stages, we have the PF, the first and last cycle. And then you've got all your data here for your pump selections. And then as far as showing the brine and permeate quality, we show the first cycle, the last cycle, and the PF flush, similar to traditional, which is, you know, the first, second, and third stage. And then for the element details, we show each cycle and then each membrane, similar to traditional, which is each stage and then each membrane in that stage. But the difference is, you know, we could have 50 cycles, which becomes a long report, but I like having that information. And as far as what we're showing, it's the same as traditional. There's a help section if you want to go in. I know some of these terms are new, and I probably didn't highlight all of them. So you can go in and look at the definitions, pretty detailed help section. And the last 2 minutes here before we leave some time for Q&A, I just want to show a screenshot of CCRO on the left and then traditional on the right. So you have these CCRO inputs. Most of the time you don't have to change them. I just want to highlight the simplicity and the value of our system. So these two systems are identical. This is actually a project that we're working on, 4 trains, 50 pressure vessels each. So everything is identical as far as number of membranes and permeate flow rate. But you'll see CCRO has better permeate quality, and that's because you have the concentrate recycle with traditional. And the reason you have to have that is to get any cross flow on your last pressure vessel, your last stage. You need more feed water, and that increases your pressure and decreases your permeate quality. And because we of our semi-batch process, we have a much lower average pressure, and that translates into tremendous energy savings. So you can see the power savings, 4.4 versus 5.8. The beta and the cross flow rate, I managed to get them the same, but for CCRO, to decrease your beta, increase your cross flow, again, you just go into your cycle recovery, which directly controls your circulation pump. It's independent of recovery and everything else. So I just dial that at 35%, and I can get as much cross flow as I want. You can change that set point on your iPhone or your smartphone. Where a traditional system, I've got permeate throttling in each stage, trying to force some more water to the last stage, the concentrate recycle. And then this is the feed TDS in this application was almost 3,000, and pushing 93.5% recovery. I have no pressure left for the last stage, not even the second stage. So I've got two booster pumps. So from a design and operational standpoint, you can see the complication with the traditional system and the beautifully simple CCRO process. So we're running out of time here. So we've got about 7 minutes, and I'll hand it over to Leanne for Q&A.
Thank you for sharing that with us, Brent. That was really informative, and it's causing a lot of people to write in questions. So we're going to try to get through as many as we can. And I encourage everyone, if questions have popped up or pop up as we're answering some more, please feel free to type those into the questions box, and we will get to as many as we can. First, just a couple housekeeping things. Brent, could you please show us where on the Desalitech website people can view that how it works video, if they'd just like a basic overview of how CCRO works?
Sure. So I just paused my screen. I don't know if you can see it right now. I'll unpause here. Okay, you should see the website. Yeah, so here's the CCRO button, and it's on the home page. We won't play the whole video here, but it's just a kind of a like a whiteboard, simplistic video to explain the process.
Great, thank you. And Alan, where's the best place to download this program, and is there a cost or fee?
The best place to download is to go right to the Lanxess website. The business unit that has this software is called Liquid Purification Technologies. So you will see an LPT tab, and inside the LPT section of the website is a tab on LewaPlus. You also can go to www.lewabrain.com and download from there. And the program is free. Provided as a service to the industry. So no cost. It is licensed. You do need to give us your email address so we can send it to you. That's it.
Thank you, Alan. Looks like we have one for Brent here. Brent, can you save your water analysis in the program? And what about if you're working on multiple projects? Can you save multiple documents? Brent?
Okay, I'm unmuted here. Yeah, I'll pull up the program. So that's why I was saying we should just all stay on mute because we keep forgetting. Unmute. Yeah, so it's a little bit different that you actually save the program you actually save the actual projections each run in the program, and then you import and export. So if you want to share them, you of course export or import the files, and it's super easy to do.
Excellent. Okay, we have another one here. Looks like this one is also for Brent. Will Desalitech guarantee the recoveries that I see in this program?
Yeah, so the program has guidelines for recovery, and they tend to be pretty conservative, relatively conservative. So if you're going to push the boundaries, the recommendation is to go to your anti-scaling provider and run their program scaling projections. Once you work with us and we run our own scaling projections and see the design, we'll give you a proposal, and part of that proposal will be a recovery guarantee. And that recovery guarantee is tied to the project. So if we don't hit our target, then you get the project at a discounted rate.
Oh, great. Okay, and actually we have another one coming through here that is related. How is the maximum recovery determined with regard to anti-scaling? Using CCRO, the higher percent saturation can be achieved for any given anti-scalant, or for instance, if a product limit for calcium sulfate may be 300% for saturation concentration for conventional RO, and with CCRO, is there some higher limit, like 400 or even 500, and how is that determined?
Yeah, so what we tell people, if they're going to run their own scaling projections, we just tell them, we tell people to run them to just 100% saturation, or to the maximum the program allows. So that maximum in a traditional system would be, a red flag. Typically, you would only design to 80% to give yourself a buffer. But the 100% saturation, or the pushing the limit of the scaling projection, that's the bottom of our guarantee. And we will guarantee past that, but it's on a case-by-case basis, just because the interaction with all the different ions, the chemistry is different every time. So it's a case-by-case basis, and you'll just have to contact Desalitech.
Okay, thank you. And we have a lot of questions coming through, so if you both are okay to stay on past the top of the hour.
Problem.
Okay, great. So we have one here. Why is some of the information highlighted in orange on the report? What's the reason for it being highlighted in orange? And can you give us an example?
Brent, you want to tackle that, or should I?
Sure. Yeah, the orange, that's just the input. So if it's grayed out, it means you don't have access. So like for the CCRO inputs, you need to click on configuration to change those set points. Again, most of the time you don't have to. So you just set your recovery, your membrane parameters. These are just default settings based on your feed quality. Stick in your permeate rate, set your flux with the number of pressure vessels, pick your membrane, and you're done. And of course, that recovery, if you're going to push the limits, you've already run that with your scaling projection software.
Aha, okay, thank you for clearing that up. Okay, and we have another one. Can this software calculate ISD, internally staged design arrays? Sounds like that one's for Alan.
I think in the classic program, yeah, we can do that. I'm not sure I know how to answer that one, though. I'd like to respond directly to the person who made that inquiry.
Sure, we will get you both in contact with each other. And Brent, why is the minimum time for the closed circuit loop 5 minutes? That seems like it might be a long time.
Yeah, we have pushed that boundary. So it's just a conservative set point that we put in the program for people to follow. But we have gone below that for sure. So it's changing, it's flipping between the closed circuit and PF mode. So the pumps are ramping up and down, and the brine valve is opening and closing. So ideally we like it above 5 minutes, but again, we can push that boundary.
Okay. And does the program consider elevation in the design? What about people that have certain projects operating at really high levels of elevation?
Do you want to answer that, Alan? I'll just give you all the
Yeah, I think we simulate that elevation by actually using permeate throttling, and we put a pressure into the permeate line, which would approximate the height of water that would be representative of the height in the system. And Brent, you can, I think, highlight that. See permeate throttling there, you clicked it, and what happens is the cell becomes cream colored as opposed to grayed out. And that allows you to, once you click permeate throttling, you can now put a pressure into that line, and that will impact the feed pressure of the overall system, and it is representative of a height dimension in an overall actual field condition. I hope that's a satisfactory answer. Tricky one.
Thank you, Alan. And Brent, why should the concentrate flow for the closed circuit and the plug flow be almost the same?
Yeah, so that's not critical. It's just a rule of thumb that I like and that engineering likes. You could argue that closed circuit is probably more important. So during closed circuit, you're running at high recovery, so you want the high cross flow to keep your betas down. And then during PF, I just like having the extra energy and turbulence in there to really just blast out the concentrated brine. So during the flush, you can actually dissolve some of the scale. So if things have started to precipitate out, you know, the low TDS flush helps dissolve that, but at the same time, just the extra energy and turbulence to try to just blast out that brine, and anything that wants to precipitate out that extra energy of just, again, blasting it out the door is beneficial.
Okay, thank you. And we do have a few people asking fairly specific questions, so what I'm going to do is put Alan or Brent in direct contact with those of you who are asking about some specific projects. I think that will be the best path here. And quick question, looks like this is for Alan. Giving Lewa's presentation, are there things that you do differently for their projections? I'm assuming that means CCRO versus other membrane supplier projections?
I'm not sure I understand the question precisely, Leanne. The membrane algorithms that we are using are common between both the CCRO and the classic RO modules. So I don't know if there's anything that we're doing different other than modeling each process in its own unique way.
So it may be referring to the design guidelines as well. So the design guidelines I should have highlighted are the same for traditional and CCRO. So for example, you know, concentrate flow per pressure vessel, you know, with wastewater reuse, if you go below 18 GPM per pressure vessel, you'll get that flag. You'll get that flag in CCRO, and you'll get that flag in traditional. So one thing to remember with CCRO, so say lead element flux, if you overflux that first element, well, first of all, we have much better flux distribution because you have 5 membranes in a 1-stage system versus, you know, 3 stages, 15, 21 membranes. The advantage, or the thing to consider when you that high lead element flux, it may only be the last 1 or 2 cycles versus a traditional system. You know, you're going to be overfluxing that first membrane 24/7.
Brent, let me add to the design guidelines.
Sure.
One thing I would point out on the design guidelines is each membrane manufacturer does generate their own set of design guidelines. But frankly, these guidelines have been more or less the boilerplate of the industry for the last 30 years. So Although there are subtle differences between them, they're pretty much interchangeable, as are the elements, as pretty much drop-in replacements for one another. There's also a little tab on the design screen that will bring those design guidelines up to view. So while you are working on the design screen, if you have a question about what the true design guideline is for a label brand element, you can bring that right up by clicking. Brent, it's that you see on the right above the graphic. There you go. If you click on that, that will bring the design guidelines right up. They come right out of the help section.
Okay,
and
perfect. I think this is answering the question. Yep, great. That's a helpful little tab.
It brings the keys to the kingdom.
And hey, Brent, we have someone asking, what's the highest salt supersaturation that CCRO can achieve, even if it's briefly?
Yeah, I mean TDS. It depends on what's in there. So I like using silica as an example because people are familiar with that and it's a challenge. So again, with silica, I can tell you 300 ppm is kind of the guideline with antiscaline and neutral pH, and we've pushed that over 500 and run consistently without seeing an increase in pressure. So the max concentration factor, max TDS, I mean, it's a function of pressure. So whatever we can do, if we're not limited by scale, we can go up to the 600 psi. I think if that was the question.
Oh wow, yeah, I think that answered it. Thank you so much. And now looks like we're about almost 10 minutes past, so we're going to go ahead and wrap up. But Brent, if you could actually just flip your screen back to your last slide with your email and Alan's email address on it. I'd like to invite everyone with more specific questions to please feel free to email Alan or Brent specifically with any questions. And for those of you who have already asked specific questions, we will go ahead and put you in contact with them directly right after the webinar. So we'd like to, at this point, conclude the webinar. Thank you, everyone, for joining. And again, we really do strive to answer everyone's questions, so please do feel free to email any of us directly. Thank you, Brent, for your time. Thank you, Alan, for your time. This was very informative.
Thank you.
Thank you.